Now we're going to be looking at what's called Pythagorean identities. The reason why they're called this is because you have two things that are being squared and added, much like in the Pythagorean theorem, which says a squared plus b squared equals c squared. We will also be using that theorem to prove what each of these expressions simplify to. So first we have sine squared of x plus cosine squared of x. The question is, does this equal anything? And if so, what does it equal, and can it be simplified? That's what we're going to show in this proof. So the first thing we're going to do is we're going to break down sine squared into sine times sine, since that's exactly what happens when you square something. Next, we're going to break down cosine squared into cosine times cosine, since again, that's exactly what happens when you square something. Next thing we're going to do is note that sine of x can be rewritten as opposite over hypotenuse, because that's what its definition is. Same thing for here. Cosine can be written as adjacent over hypotenuse, since that's the definition of cosine. Same thing for this cosine right here. So for the third line, all we're doing is writing out the definitions of the trig functions. Now we're going to take note that we have two opposites on the top of the fractions and two hypotenuses on the bottom. So this will now simplify to opposite squared divided by hypotenuse squared. Okay, and in the same way, for the cosine, we have a's on top and h's on bottom, so that's going to become a squared over h squared. So for the first page of our proof, we've just shown that sine squared of x plus cosine squared of x can be simplified to opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. Okay, so now what? Well, notice that both of these denominators have an h squared in them. So we can in fact combine these fractions now and just have opposite squared plus adjacent squared in the numerator with one denominator as h squared. I'm going to go ahead, I did have a separate page, I'm going to go ahead and do it on the same page here so that we don't lose sight of what's happening here. So that's going to morph into one single expression. Now, this is where the Pythagorean theorem comes in. Let's look at a triangle here, okay? And let's say that this is our angle right here, theta. This is going to be a right triangle, so I'm going to go ahead and put its little symbol right here. Now notice that if it's a right triangle, then if you square the two legs, they equal to the square of the hypotenuse. That's the definition of the Pythagorean theorem. So therefore, in this particular case, our opposite side squared plus our adjacent side squared is equal to the hypotenuse squared. Well, let's go back to what we have so far in our little proof. We have opposite squared plus adjacent squared on the top of the fraction. Well, we've just proven with the Pythagorean theorem that that's equal to h squared. So the next part of our proof is really simple. This opposite squared plus adjacent squared can easily be substituted with with h, because opposite squared plus adjacent squared is equal to h squared. I'm jumping ahead of the proof here. And so we still have an h on the bottom of the fraction. And what does h over h equal? Well, if you take anything and divide it by itself, it's equal to 1. So we've actually just proven that with all of these steps, that sine squared plus cosine squared, once it's all said and done, is just equal to 1. And that is the last thing I'm going to write for this proof. We have now proven that sine squared of theta, or x or whatever, plus cosine squared of theta is equal to, and we'll use the color red again, 1. And that's always going to be the case, simply because of that simple proof, and because we use the Pythagorean theorem, we call it a Pythagorean identity. That's it for our first proof of sine squared plus cosine squared is equal to 1. If you have any other questions about this, let me know.